Rutherford, when he was working in around 1909, wanted to show that Thomson's model was correct because he believed that this was the correct model. There were other people proposing ideas of how this could be and how the material could be spread out or distributed in the atom, but none of them had any basis to support it. And so Rutherford had a hypothesis. He said, if Thomson's plum pudding model is correct, then alpha particles should pass through a piece of gold foil unaltered because there was no dense positive area to change the path. And so he planned an experiment. And in his experiment, he wanted to use alpha particles, a type of radiation. Now, as an aside, as we said, he started off at Cavendish's lab under Thomson. Then he went to work in McGill. And his work at McGill was pivotal for him to be able to do his gold foil experiment. Because for him to do his gold foil experiment, he had to have an alpha particle. He needed a positively charged form of radiation so that he could investigate how the positive material of the atom was spread out. Well, this was done when he was in McGill working with a grad student that he picked to work with him by the name of Harriet Brooks. Now, Harriet Brooks was the first female to get a master's at McGill in physics. Okay? Rutherford said that she was as good a researcher as Madame Curie. And for a little while, in the early 1900s, after she had finished her master's with Rutherford, she went off to work with Madame Curie, and then she came back to Rutherford's lab. And she looked at the radioactive decay of radium and showed that in the process, it gave off alpha particles, which was a charged helium atom. This was pivotal for Rutherford's gold foil experiment. Now, unfortunately, Harriet Brooks, because of the time that she was in, after she had finished doing a series of experiments and setting things up, when she got married, she decided to no longer do any research. But if she had continued working, she could have really contributed to the field. And it's at a loss that she decided to stop working at the time. So let's go back to Rutherford's gold foil experiment. Now that he has his alpha particle, his positively charged radiation, he has a source of it. He has a focus slit, so rather than it coming out as a spread out beam, it comes out as a single slit, single beam. And then we have a piece of gold foil that we're going to bombard it with. And Rutherford said that this beam will just pass through and hit the screen behind it. So he had a screen that lit up every time an alpha particle hit it. So he would be able to see where all the alpha particles hit it. And he predicted that all of these alpha particles would go right through and hit the screen here. Well, it just so happens we have a way to simulate Rutherford's experiment, so let's take a look at that. Okay, so let's take a look at this simulation. So in a simulation, just like Rutherford had, we have our source of our alpha particles. We have our piece of gold foil that we're going to fire them at. We have our screen that can detect. And what we have down here at the bottom is we have just the screen uncoiled and spread out. Now, if Rutherford's hypothesis is correct, most of the particles should hit right here at 0 in this small area. We should find no particles outside of that range because they'll all pass through. So let's start it up. And we can already see that the red lines, some are not going straight through. We see here at the bottom, we have our green dots, and they show where the particles hit. We can see the vast majority of them are going through, but some are deflected. So let's let it run for a couple minutes, and then we'll come back and we'll see what we have. So now the simulation has run for a couple minutes, and what we can see is, yes, the vast majority of my alpha particles went through and had their paths unchanged. We have a whole bunch who are changed by just a little bit. We even have some that are changed by a lot. And so this suggests that Rutherford's hypothesis is not correct. So as we saw, some of the particles did not pass straight through. A good chunk of them did, but some of them were deflected and some of them were reflected. These results shocked Rutherford. In fact, he said that it was as if you fired a 15-inch cannonball shell on a piece of tissue paper and it backed up, came back and hit you. Now, Rutherford was one for clipping statements. In fact, he was also known to say physics is the only science, all other sciences stamp collecting. This was just before he got the Nobel Prize for chemistry. So it probably really bit at his crawl that he didn't get it for physics. But you have to understand when he said this. He said this in the early 1900s, at the time where physics was probing the structure of the atom, and yet chemistry was still trying to figure out all of the elements that are out there, and biology still at this point didn't know a lot about genetics or anything else that contributes to modern biology. So at the time, his statement sort of makes sense. As a result of his experiment not going the way that he had predicted and it showing that his hypothesis was incorrect, Rutherford had to reinterpret his results. And what he said was that in the center of the atom, there must be a positively charged particle. This positively charged particle was responsible for changing the path of his alpha particles. And he said all the positive material is not spread out, but it's condensed in the center of an atom, and he called this center of the atom the nucleus. He also said that the electrons were somewhere around the nucleus, and he said that the atoms were mainly empty space. And the reason he said they were mainly empty space was because most of the alpha particles still went through unaltered. He called his positive particle the proton some years later. But he also at the time predicted that there has to be a third particle that has no charge, because this is what allowed the atom to have most of its mass. He could only account for half of the mass of an atom with his protons. Well, so his model we call the nuclear model because we have our protons in the center in our nucleus and we have our electrons somewhere around. One of Rutherford's compatriots, Chadwick, who was one of his colleagues and worked with him, ultimately did discover the neutron. He discovered it in the 1930s. Okay? And he discovered it while studying isotopes, which are two atoms that have the same number of protons but different numbers of neutrons, or a different mass. So I have two atoms with the same number of protons, but one's heavier than the other. And Chadwick was also able to show that the neutron was in the center of an atom. So now we have Rutherford's nuclear model. We have the neutron in the center with our protons. We have our electrons somewhere around. Rutherford's model had some flaws in it that violated some classic physics. The big one being, why don't the electrons fall into the nucleus? Because we have positively charged particle in the nucleus, we have a negatively charged particle around it. So why is this electron not falling into the nucleus?